Albert Einstein did not win the Nobel Prize because of relativity. The 1921 Nobel Prize in Physics was handed to the German ambassador in Sweden, Rudolf Naldoni, who received the prize on behalf of the actual awardee, Albert Einstein. Einstein did not even go to receive the prize in person. The prize was not even for his most famous theory, relativity, but rather for explaining the photoelectric effect. And here you are thinking the same questions I thought. First, why didn't Einstein go to receive his prize? Second, why wasn't the prize awarded for relativity? A third question is, why is the photoelectric effect important enough to earn the Nobel Prize?
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
To understand this gossip about the Nobel Prize, we need to go back to 1905. This is the most important year of Albert Einstein's scientific work. As a physicist, he worked in a patent office writing 3 revolutionary papers. The first was showing that the idea that atoms exist explained a mysterious phenomenon called Brownian motion, essentially proving that atoms exist. You probably didn't know that Einstein did this. The other 2 papers are the focus of today's video. One is the paper laying the foundation for the theory of relativity, and the other is about the photoelectric effect. We'll continue with relativity, learn about the theory, and why the Nobel Committee refused to award a Nobel Prize for this theory. The theory of relativity is named as such because it arose from the study of how electric and magnetic fields interact when they are in relative motion. The physical problem that underpinned the development of the theory was basically the following. What is the electric and magnetic field generated by a moving electric circuit? Studying this problem and new hypotheses, experiments in the late 20th century showed Einstein created methods to calculate moving electric fields. Thereby, he created the theory of special relativity, which has 2 fundamental postulates. The first postulate is the postulate of relativity, which states that the laws of physics are the same for all observers moving at a constant speed. If you do an experiment standing on the ground or in an airplane moving steadily, the result has to be the same. It is when we include acceleration that the experiments start yielding unexpected results. And the second postulate is the speed of light, that the speed of light in a vacuum is constant for all observers, always 299,792,458 meters per second. Whether you're on a plane, on the ground, or on a roller coaster, you always measure the same speed for light. And that is very, very strange. And it is especially strange if we remember that all other speeds we can measure depend on your relative motion. If you watch a 100-meter dash while standing still, the relative speed between you and the runner is around 30 kilometers per hour. The relative speed between 2 runners in the same race is almost 0. They are basically stationary in relation to each other. Speed depends both on who is being measured and who is doing the measuring, except for the speed of light. And to ensure that the speed of light is indeed universal, Einstein had to sacrifice the universality of other things. Everything has a cost. In the theory of relativity, distances depend on the speed of the person measuring them. The 100-meter dash is 100 meters standing still, but for the competitors in the middle of the race, it is just under 100 meters. For us, standing still, the Earth is more than 12,000 kilometers in diameter. For a particle at almost the speed of light, the Earth is just over 500 kilometers in diameter. The same goes for time. The rate at which time passes depends on the speed of the clock used to measure time. And the rule that determines the contraction of space and the dilation of time is as follows. These effects happen in order to keep the speed of light constant and absolute. Without these effects, the speed of light would change from observer to observer. If you find this strange, then congratulations. You think like most of the physics community did at the beginning of the 20th century, especially the Nobel Committee. Einstein's theory of relativity was received quite lukewarmly. It was quite controversial, faced a lot of criticism, and required more experiments to prove. Testing this new theory of Einstein rigorously would not be easy, since there was no obvious experiment to be done. And the Nobel Committee considers robust experimental evidence essential for nominating someone. Because of this, Einstein's chances of being nominated for relativity in the near future were quite low. And to make matters worse, when the theory of special relativity was established in the scientific community, Einstein published his second theory of relativity, which was general relativity. And general relativity indeed presented a new theory of gravity that was much more mathematically complicated than the first theory of relativity. So, in the view of the Nobel Committee, relativity needed more experimental evidence to deserve an award. Therefore, starting in 1912, Einstein began to be recommended almost annually to receive a Nobel Prize. And in 1917, the Nobel Committee felt quite pressured by the community of physicists to award Einstein. And to understand the Nobel Committee's solution, we need to go back to another paper published by Albert Einstein in 1905, his miracle year. Einstein changed the world's view on light twice in 1905. One was with relativity, and the other was consolidating the idea of quanta of light, the idea that light exchanges energy in packets and not continuously. But before delving into this revolutionary hypothesis, we need to understand its motivation, the black body problem, and Max Planck's solution to this problem. The black body is a useful approximation of the behavior of many different things from the sun to human beings. A black body is like a black box of radiation. It absorbs all the electromagnetic radiation, or light if you prefer, that falls on it, and then emits all that energy back as heat. So, all a black body does is absorb and emit light. Simple as that. The black body problem was as follows. What are the frequencies and amounts of radiation that a body emits at a given temperature? If you use classical physics, you get an absurd answer. The black body emits an infinite amount of extremely high-energy light. Planck solved this problem by postulating that the black body does not emit energy continuously, but emits energy in small packets. Rather than the radiation coming out of the body being like water flowing, it was more like drops dripping one by one. And this discrete behavior, with things happening in discrete steps, is precisely what we call quantization. Planck quantized how the material of the body could emit energy and solved the black body problem. And he discovered a new physical constant called Planck's constant, which we represent in physics by the letter h. At the time, he thought that this constant was just a constant of the specific black body problem, but it will be very important in the future. Einstein read this article in 1905. He thought of a better way to solve the same problem, with simpler mathematics than Planck's. And for that, he created a new hypothesis of quantization. Instead of quantizing the emission of energy, Einstein quantized light. Einstein said light carried energy in discrete quantized packets. It was like light behaved like a gas of light particles. And using this model of light gas, Einstein solved the same problem as Planck, succinctly. But Einstein didn't stop there. He proposed that light behaved in a quantum manner in general, and that other unresolved physical problems could be explained through the quantum behavior of light.
And the rest of his article is focused on using this same hypothesis to solve another open problem, the photoelectric effect. The photoelectric effect is the basis of modern solar panels and the phenomenon in which electric current is produced when light hits a metal. In other words, light hits a metal plate and the light energy expels electrons from the atoms that make up the metal and sets them in motion. Philippe von Leonard found something strange in the photoelectric effect. The energy of electrons moved by light didn't depend on light intensity. Which means, if you add more light, you get more electrons moving, but all these electrons have the same individual energy. You only get electrons with more energy if you use higher frequency light. The frequency determines the type of light hitting the metal. Visible light has a frequency between 400 and 700 terahertz. 1 terahertz is 1 trillion vibrations per second. So, visible light vibrates more than 400 trillion times per second. Radio waves have frequencies that are thousands or millions of times lower. The photoelectric effect requires a minimum frequency for current. Low-frequency light doesn't affect the metal. And this is strange because the energy of light is determined by both the frequency and the total intensity of the light. Two situations where light carries the same energy produce different results if the frequency of the light is different. And Einstein explained this with his quantum hypothesis of light. Light only carries energy in a quantized manner. Instead of depositing energy continuously into the metal, it deposits it little by little in packets of energy, which we now call photons.
And the energy in each photon of light is determined by its frequency times Planck's constant. Therefore, low-frequency light is composed of low-energy photons. These low-energy photons cannot interact with the electron due to the lack of energy in the packet. Increasing the intensity of the light does not increase the energy of the photon, only their quantity. But since no individual photon can move the electrons, nothing happens. And when the photons have enough energy to move electrons, each electron absorbs the energy of a single photon. The individual energy of the electrons is set by the energy of the photon, which depends only on the frequency of the light and not on its intensity, as the experiment showed. Einstein and his hypothesis of quantization met resistance similar to relativity, with Einstein explaining the photoelectric effect. But Einstein didn't stop there. Between 1905 and 1912, he published several articles explaining more and more experimental results with his quantum hypothesis. Not to mention that experiments with light and electric currents were much simpler to conduct, which quickly provided many experimental evidences for the hypothesis of light quantization. And just to make one thing clear, at that time physicists did not believe that light was actually made of photons, but only that it behaved as if it were. The idea that photons themselves are real only came about in the late 1920s. The explanation of the photoelectric effect through quantization had two notable effects in physics. The first was to help establish the process of quantization is common in nature and that Planck's constant isn't just for blackbody radiation, but a universal constant. And the second was to give Einstein an innovative theory that was well proven experimentally, which the Nobel Committee wanted. In 1917, the Nobel Committee planned to award not only Einstein, but the trio of physicists who started quantum physics. In 1918, Max Planck won the Nobel Prize for his solution to the blackbody problem. In 1921, Albert Einstein won the Nobel Prize for explaining the photoelectric effect and contributing to theoretical physics. And in 1922, Niels Bohr won the Nobel Prize for atomic structure. And together, these three Nobel Prizes crown not just the three most respected physicists of the time, but also the new field of quantum physics. And now only the last unanswered question remains. Why didn't Einstein go to collect his Nobel Prize? And the answer is because he was traveling in the East, and he didn't want to return to Europe before the trip ended. At the time, he was quite famous outside the physics community and too busy to receive a Nobel Prize. What would you do if you were Einstein? Would you accept the Nobel or continue with the trip? Type your answer in the comments.